From sci-fi movies to the barcode scanner at the grocery store, lasers are just everywhere. And they really do seem like pure magic, don't they? A perfectly straight, intensely powerful beam of light. But it's not magic, it's physics. And honestly, it is absolutely fascinating. Okay, let's dive right in. So, how does it actually work? How do we take the chaotic, jumbled up light from something like a regular light bulb and somehow tame it, organize it, into that iconic razor sharp beam? Well, that's the big question we're going to answer together. And here's how we're going to do it. First, we'll break down what the name laser even means. Then, we're going to take a trip back in time to a brilliant idea from Albert Einstein. We'll uncover the secret to making a sort of light avalanche, see how you actually build one of these things, and finally, we'll look at a couple of real-world examples. So, first things first, what exactly is a laser? Well, believe it or not, the entire answer is hidden in plain sight, right inside its name. See, laser is actually an acronym. It stands for Light Amplification by Stimulated Emission of Radiation. And this isn't just some boring label. It's literally the entire instruction manual for how a laser works. We're about to unpack every single one of those words. But before we get into the how, let's talk about what makes laser light so darn special. It really comes down to these four amazing properties. It's monochromatic, which just means it's one pure color. It has high intensity, because all its power is focused on one tiny spot. It's got high directionality. It stays in a super tight beam for really long distances. And maybe most importantly, it's coherent. That means all the light waves are marching in perfect lockstep. These four things together are what let lasers do incredible stuff, like cut steel or read the tiny pits on a Blu-ray disc. Now, to really get how we create those properties, we have to go all the way back to 1917, to a paper written by Albert Einstein. He actually predicted the physics of how light and atoms talk to each other, laying the entire groundwork for the laser decades before anyone even built one. He basically described this three-step atomic dance. So first up is what's called stimulated absorption. Just imagine an atom chilling out in its low-energy ground state. If a photon of light with just the right amount of energy comes along, the atom can absorb it, kind of like eating a snack, and use that energy to jump up to a higher, excited state. Simple enough, right? The atom just eats the light. But here's the thing. That excited state is unstable. The atom can't stay there forever. So after a tiny fraction of a second, it'll just randomly decide to fall back down to its ground state. When it does, it spits out the photon it absorbed. This is spontaneous emission. But notice, the photon just flies off in a completely random direction. This is exactly what's happening in a normal light bulb. It's totally chaotic and messy. But this is the stroke of genius. This is the part that makes lasers possible. Stimulated emission. What if a photon comes along and finds an atom that's already in that excited state? Well, instead of being absorbed, this photon can actually nudge the atom, stimulate it, causing it to fall down and release its own photon. And here is the absolute key. The new photon is a perfect clone of the first one. Same energy, same direction, same phase, everything. This is where those four special properties are born. One photon becomes two identical photons. Okay, so this is the crucial part. We now have a way to make two identical photons from just one. This is the amplification part of laser. So the big question is, how do we make this process, stimulated emission, the main event, instead of all that random, spontaneous emission? We basically need to rig the game. We have to stack the deck. We have to create a really specific and, frankly, a very unnatural condition inside a bunch of atoms to guarantee that when a photon comes along, it's way more likely to cause stimulated emission than anything else. We need to kick off a chain reaction, a literal atomic avalanche. And the secret sauce to do that is something called population inversion. You see, normally, most atoms are lazy. They're in that low-energy ground state. But what if we could flip that upside out? What if we could create a scenario where the majority of atoms are all pumped up in that excited state? Well, that is population inversion. It's kind of like having a whole mountaintop full of skiers just ready to go, waiting for that first one to start an avalanche. Okay, so we've got the theory down. Population inversion is the key to starting that chain reaction of stimulated emission. So, how do we actually build a device that does this? Let's talk hardware. Turns out, you really only need three essential parts. First, you need an active medium. This is your collection of atoms. It could be a gas, a crystal, whatever. That's going to do the actual lasing. Second, you need a pumping source. This is the energy you pump into the medium, like a bright flash of light or an electric current, to create that all-important population inversion. And third, you need an optical resonator. This is just a fancy name for two mirrors placed at either end of the active medium that trap the photons and bounce them back and forth. So we have our three ingredients: the active medium for the atoms, the pump source to get them excited, and the mirrors to build up that avalanche. Now let's see how they all come together in a couple of real-world laser designs. On the left, you've got a classic helium neon gas laser, one of the first types ever made. And on the right, a tiny little semiconductor laser, the kind you'd find in a Blu-ray player or a laser pointer. They look totally different, but they both use the same three core components we just talked about. Now, what's really cool here is the clever teamwork happening inside the helium neon laser. The pump source, an electrical discharge, it excites the helium atoms. But the helium atoms don't actually make the laser light. Instead, they act like little messengers, bumping into the neon atoms, which are the active medium, and transferring their energy in a perfect little handoff. That's what creates the population inversion in the neon. It's just a brilliant piece of atomic engineering. And then you have the semiconductor laser. In this case, the active medium is a teensy-weensy crystal junction where two types of material meet up. The pumping source is just a simple electrical current, and that creates the population inversion right there at the junction. This incredibly compact design is what makes them so efficient and so common. They're the workhorses of modern tech, powering everything from fiber optics to barcode scanners. And there you have it, from a theoretical twinkle in Einstein's eye to a whole universe of applications. The laser is just an amazing testament to our ability to understand and control the quantum world. We've gone from chaotic, messy light to a perfectly ordered beam, all just by choreographing an atomic dance. Which, of course, leaves us with one final thought. Now that we can amplify light with this incredible precision, what's the next frontier we're going to illuminate?